Hi all. So in this unit 2, we are in the last stage, that is power dissipation, low power design principles, and examples of combinational logic design circuit families. Okay, right. So so far we have seen what is static CMOS logic and what are all the design styles and how we can design the different digital logic circuits using domino and dual rail configurations, right? And the main thing is power, is it right? So whenever we are increasing the number of transistors, it consumes more power. So every VLSI design engineer must ensure the power as well as area and speed, so performance. Okay, so so we need to design a optimized and less optimized design, as well as we have to reduce the number of transistors. As much as we are reducing, we may get yeah, less area and less power, as well as we are getting quick response, that is time also it will get reduced. Okay, so every VLSI engineer must have a thought to design each and every single circuit, how to optimize the circuit using the transistors. Okay, for that they're having we need to follow the some design principles. Okay, so that we are going to see in this video. Okay, then what are the power dissipation are there? So you're having four major power dissipation: static power dissipation, dynamic power, leakage power, and short circuit power. So this will happen each and every stage of the circuit. Okay, and static power will deliver when the device is on. Okay, but it's not in the operation. So that time there will be some power dissipation is there. When the transaction happens, when 0 to 1 and switching happens, no, so that time it delivers the power, dissipates the power, that is dynamic power. And leakage and short circuit power, that is very very minimal, even though that cause a huge amount when we are going for millions and lakhs of transistor in a single chip. So we might have considered about these four power dissipation factors while designing any integrated circuit. As all we know, uh, inside the IC we have a transistors, right? So what transistors we are having? That is MOS transistor, that is CMOS transistor, a combination of both NMOS and PMOS combination transistors we are having. Okay, then uh, in the transistor, if I am taking for example simple adder circuit, it will simple full adder circuit, if I am taking now, around 24 transistors will come. Okay, a simple adder to add single bit for getting sum and carry value. So imagine we are doing you're doing it I10 processor value, so the manipulation it's huge. So it will take millions of transistors in a single chip. Okay, so it delivers the power, delivers the enormous powers. So we have a various low power design technique to reduce the power dissipation. Okay, so what you have seen in previous one, for that four power dissipation, how each technique you are having different scenario. Okay, here before fabricating, okay, before fabricating the integrated circuit, we may have many steps. Okay, like a design entry and go for simulation, synthesis, validation, FPGA validation, then ASIC design flow. Okay, so we need to follow all those design steps, then only we can go for a fabrication. Uh, then the first transistor was fabricated in 1940s. We may have a term called Moore's law, right? So what he states that, so Moore states that every 18 months inside a chip, the transistor will double, which means every 18 months that inside the chip there will be a transistor, no, that transistor will double. For example, now it's 2020. For example, I'm taking 100 transistor in a single chip. In 2040 it will increase, in a double. Okay, that's what he stated in 1975. Like that only it's happened. And now we are now for 4 nanometer technology. So they have started with 180 nanometer, then 90 nanometer, and 45 nanometer, 32 nanometer. So like that they are step by step they are reducing the nanometer size. What it says, the nanometer, that the source to drain channel width. When you are going for fabrication, we are having a channel width, right? That when we are reducing the channel width, automatically your transistor size will reduce. Okay, if size is reduced, we can accommodate a more number of transistor in a single chip. If number of transistor increases, we can perform the more number of operations. Okay, that main drawback is power dissipation. So we need to concentrate on this power factors. So for that we need to follow some design key principles. The first one is using the lowest possible supply voltage. So ICs we may have now maximum 5 voltage. We can take it as up to 5 voltage. So every IC working under 5 voltage, then 3.3 voltage, 1.4 voltage also their operating voltage is there. Nowadays ICs are working. So we need to choose the lowest possible supply voltage, and using the smallest geometry means space, and highest frequency device, but operating them at the lowest possible frequency. So we need to use a optimized area with the lowest frequency, and using parallelism and pipelining to lower required frequency of operation. You know about pipelining and parallelism concept. Okay, so we need to use those concept inside the fabricating ICs. Okay, so it will help to power reduce the power, and power management unit. Okay, so power management unit, what type of regulator we need to use, and how should be the circuit. So those things we must analyze, and then we need to prepare. And designing systems to have lowest resources and subsystem performance, which means we so number of transistors or number of components, whether not only transistor, resistor, capacitor, whatever things we are using, that must be in a lowest level. Okay, so minimum number of component, and we need to extract from that highest possible output. So that is a key principle of designing any integrated circuit. So we must follow these key principles to design a low power integrated circuit. Okay, and examples of combinational logic design. So in this I have taken as 2:1 mux using transmission gate. I hope you all know about 2:1 mux, right? So what is the operation? When selection line, so depends on selection line, your input it's going to the output, right? Here the S is the selection line, and A and B are the inputs. Okay, so 2:1 mux, we have two inputs, one selection line and one output. And A and B, it is given the inverting input, right? So inverting input I am giving, and I am getting the same inverting output. If I am not connecting with N1 and N2 as a non-inverting input, I am getting output Y is also a non-inverting output. Okay, so this is inverting. The circuit shows the inverting input and getting output, and this circuit is non-inverting input. So finally I am taking the if I want to take inverting output, I have to connect the inverter as the output. So that's it. Okay, so as I told you earlier, this transmission gate logic it's connected, both PMOS and NMOS are in a parallel way. Is it right? It's a parallel way. Okay, when your selection line is 0, so your A should go to the output, right? Or B is when selection line is 0, what will happen? PMOS transistor, so NMOS transistor get turned open, and here S bar, so S is 0, here S bar becomes 1. That 1 goes to PMOS transistor in the upper TG, and again same one which goes to lower TG, NMOS TG. Okay, then now I am giving 0, no, so that in this way A, it's passing through the PMOS and going to the Y output, whereas here S is also 0 and S bar is also 0, so both the transistors get turned open, so there is no way to go B to the Y. So like this 2:1 mux circuit will work in the transmission gate circuit. So one simple example for combinational logic design. Like that we can design 4:1 max and encoder, decoder, so that is possible through transmission gate. Thank you.